How did everything start from nothing? This profound question transcends science, delving into philosophical realms that challenge our understanding of existence. The concept of creation from nothingness invites us to consider the moment when the universe emerged, bringing with it space, time, and the building blocks that would form everything we see. This question reaches beyond scientific inquiry into the nature of existence itself. What does it mean to exist? What is nothingness? And how could something as vast as our universe emerge from it? In this exploration, we'll examine these questions through particle physics and cosmology, where scientists use mathematics and experimentation to approach these mysteries. Beneath these scientific investigations lies a deeper question: how can physics explain the emergence of a universe from a state where there was no space, no time, and no matter? Particle physics, the world of the very small. Particle physics explores the fundamental components of matter and the forces governing their interactions. Unlike everyday objects governed by classical physics, the subatomic world operates according to quantum mechanics, revealing a reality that defies intuition. At its core, particle physics seeks to understand what the universe is made of at its most basic level. Scientists study particles like quarks, electrons, and neutrinos, the building blocks of atoms, which are themselves the building blocks of matter. These particles are incredibly tiny, and their properties challenge conventional notions of space and time. The Standard Model represents one of the greatest achievements in particle physics. This theory describes 3 of the 4 fundamental forces, excluding gravity, and classifies all known elementary particles. According to this model, there are 4 fundamental forces. 1. The electromagnetic force, responsible for electric and magnetic effects. 2. The weak nuclear force, which plays a role in radioactive decay. 3. The strong nuclear force, which binds quarks together in atomic nuclei. 4. Gravity, not yet fully incorporated into the Standard Model. While remarkably successful in predicting particle behavior, the Standard Model isn't the final word. Scientists continue searching for a more complete theory that can include gravity and explain mysteries like dark matter and dark energy. Research in particle physics requires sophisticated technology like particle accelerators and detectors. The Large Hadron Collider, LHC, near Geneva is among the most powerful such facilities, where the Higgs boson was discovered in 2012, filling a crucial gap in our understanding. The intersection of cosmology and particle physics. The intersection between cosmology and particle physics weaves a complex tapestry spanning the vastness of space and subatomic particles. Cosmology studies the universe's origins and evolution, while particle physics focuses on matter's fundamental constituents. This synergy opens pathways to understanding not just what the universe is made of, but how it began. At this intersection's core is the Big Bang Theory, which proposes the universe started from an incredibly hot, dense state approximately 13.8 billion years ago. Particle physics enhances our understanding of this primordial moment by examining particle behavior at extremely high energies. Modern particle accelerators recreate these early universe conditions on a miniature scale. One fascinating aspect is the exploration of dark matter and dark energy, mysterious components comprising about 95% of the universe's total mass energy. Particle physicists search for dark matter particles using sophisticated detectors, while cosmologists incorporate these findings into models of the universe's structure. The study of cosmic microwave background radiation, a relic of the Big Bang, offers another example of how these fields intersect. This radiation provides a snapshot of the universe when it was just 380,000 years old, revealing insights into the distribution of matter and early conditions that inform theories in both fields. This interdisciplinary approach broadens our understanding while challenging theories in both fields. Anomalies like discrepancies in measurements of the Hubble constant drive the quest for a more unified theory reconciling the laws governing the cosmos at the largest scales with those ruling the smallest particles. The fundamental forces of nature. The fundamental forces are like the universe's rulebook, dictating how everything from galaxies to quarks interacts. Understanding these forces provides insights into everything from planetary movement to the stability of matter itself. The 4 fundamental forces, gravity, electromagnetism, strong nuclear force, and weak nuclear force, each plays a crucial role in the universe's structure and dynamics. Gravity keeps our feet on the ground and governs celestial bodies' motion. Despite its universal presence, gravity is the weakest force, yet its influence spans immense distances. Newton's law of universal gravitation described gravitational force between objects, while Einstein's general relativity refined our understanding, describing it as space-time curvature around masses. Electromagnetism is responsible for most phenomena encountered in daily life above the nuclear scale. It acts between charged particles and is the force behind electricity, magnetism, and light. Electromagnetism is far stronger than gravity at the particle level and is essential for atomic structure, chemical bonds, and signal transmission within our bodies. The strong nuclear force is the strongest but acts over a very short range. It binds protons and neutrons together in atomic nuclei, overcoming the electromagnetic repulsion between positively charged protons. Without this force, atoms wouldn't exist in their current form. The weak nuclear force is responsible for radioactive decay and certain nuclear reactions, such as those powering the Sun. It acts over an even shorter range than the strong force and is pivotal in processes that change one subatomic particle type into another. This force plays a crucial role in nuclear fusion reactions fueling stars and element synthesis throughout the universe. Scientists strive to develop a unified theory explaining all four forces within a single framework, a goal that has remained elusive. The quest for such a theory of everything continues to drive physics research. The building blocks of matter. Let's explore the particles that form the foundation of matter, the building blocks of everything tangible in our world. The Standard Model identifies matter's smallest constituents, categorizing them into quarks, leptons, and force carrier particles. Quarks are tiny particles that combine to form protons and neutrons, the components of atomic nuclei. There are 6 flavors of quarks: up, down, charm, strange, top, and bottom. Quarks are never found in isolation due to color confinement, they're always bound together in groups of 2 or 3. Protons consist of 2 up quarks and 1 down quark, while neutrons contain 2 down quarks and 1 up quark. The strong nuclear force determines quarks' properties and interactions, keeping them locked together within the nucleus. Leptons represent another fundamental particle category, with the electron being the most familiar. Like quarks, there are 6 lepton flavors: the electron, muon, tau, and their corresponding neutrinos. Unlike quarks, leptons don't experience the strong nuclear force. Electrons orbit atomic nuclei, playing crucial roles in chemical reactions and electrical conductivity. Neutrinos are elusive particles that barely interact with matter, making them difficult to detect despite being produced in vast quantities by the Sun and other nuclear processes. The Standard Model also includes force carrier particles called bosons, which mediate the fundamental forces. Photons carry the electromagnetic force, gluons mediate the strong force, W and Z bosons are responsible for the weak force, and the Higgs boson is associated with the Higgs field, which gives particles their mass. The Big Bang and the universe's beginnings. The Big Bang theory provides a compelling explanation for the universe's origin. This cornerstone of modern cosmology suggests that everything we observe today originated from an incredibly dense and hot point approximately 13.8 billion years ago. The theory proposes that the universe was once in an extremely hot and dense state that expanded rapidly. This expansion isn't like matter exploding outward, but rather the expansion of space itself. Imagine a balloon with dots representing galaxies. As it inflates, the dots move away from each other, illustrating how galaxies separate as the universe expands. Evidence supporting the Big Bang theory is compelling. One key piece is the cosmic microwave background radiation, CMB, a faint glow permeating the universe discovered by Pentjes and Wilson in 1965. This radiation is the Big Bang's afterglow, stretched to microwave frequencies by the universe's expansion. CMB observations provide a snapshot of the infant universe, revealing insights into its early conditions. Another cornerstone of evidence comes from observing galactic redshift, indicating the universe's continued expansion. This redshift occurs because light from distant galaxies stretches to longer wavelengths as the space between us expands. Edwin Hubble first observed this phenomenon in 1929, providing direct evidence that the universe is dynamic and ever-expanding. The Big Bang theory also explains the relative abundances of the lightest elements observed today. These elements formed during the first few minutes after the Big Bang in a process called nucleosynthesis, and their proportions align closely with the theory's predictions. Despite widespread acceptance and strong supporting evidence, the Big Bang theory has unanswered questions, such as the nature of dark matter and dark energy, which dominate the universe's total mass energy yet remain elusive. Moreover, the theory doesn't explain what preceded the Big Bang or the initial expansion's underlying cause. The early universe. In the immediate aftermath of the Big Bang, the universe was a hot, dense sea of energy. Conditions were so extreme that matter as we understand it couldn't yet exist. Instead, the universe contained a quark-gluon plasma, where quarks and gluons moved freely in an ultra-hot, dense environment. As the universe expanded, it cooled. Within the first microseconds, quarks started binding together, forming protons and neutrons, the nuclei of future atoms. This period, known as the Hadron Epoch, marked the universe's first step toward matter formation as we recognize it. Further cooling allowed protons and neutrons to begin forming the universe's first nuclei during nucleosynthesis, a few minutes after the Big Bang. These were primarily the simplest nuclei: hydrogen, deuterium, helium, and trace amounts of lithium. The precise ratios of these light elements, predicted by Big Bang nucleosynthesis theory, match closely with observations, strongly supporting the Big Bang model. However, the universe remained too hot for electrons to bind to these nuclei to form neutral atoms. It wasn't until approximately 380,000 years after the Big Bang, during recombination, that the universe had cooled enough for electrons to combine with nuclei, creating the first neutral atoms. This event dramatically changed the universe's structure, allowing light to travel freely through space for the first time, releasing the cosmic microwave background radiation. The formation of the first neutral atoms marked the universe's transition from a plasma state to one that could eventually support stars, galaxies, and planets. Gravity began pulling matter together, forming gas clouds that would become nurseries for the first stars. Evidence for the Big Bang. The cosmic microwave background radiation, CMB, stands as a monumental pillar of evidence for the Big Bang. This faint glow filling the universe is the afterglow from shortly after the Big Bang, cooled to microwave frequencies by the universe's expansion over billions of years. Measurements by satellites such as COBE, WMAP, and Planck have provided a detailed picture of the early universe, showing slight temperature fluctuations corresponding to regions of slightly different densities. These fluctuations seeded all future structure, the galaxies, stars, and planets filling the universe today. The universe's expansion itself serves as direct evidence for the Big Bang. Hubble's discovery that galaxies are moving away from us in every direction, with their speed proportional to their distance, suggests the universe is expanding uniformly. This implies it was once far smaller, hotter, and denser, as the Big Bang theory predicts. The abundance of light elements provides another key piece of evidence. The Big Bang theory predicts the production of hydrogen, helium, and traces of lithium during the first few minutes after the Big Bang. Observations of these elements' relative amounts closely match the Big Bang model's predictions. The large-scale structure of the universe, observed through the distribution of galaxies and galaxy clusters, also supports the Big Bang theory. Galaxies aren't randomly distributed, but instead form a vast web of filaments and voids consistent with the gravitational growth of initially small fluctuations predicted by the theory. Quantum fluctuations and particle creation. Quantum fluctuations, a phenomenon deeply rooted in the quantum realm, play a pivotal role in the cosmos's fabric. These are temporary energy changes at a point in space, as dictated by Heisenberg's uncertainty principle, which states that certain pairs of physical properties cannot both be precisely measured simultaneously. In the vacuum of space, quantum fluctuations occur spontaneously, with particles and antiparticles popping into and out of existence. These virtual particles that exist briefly before annihilating each other. Despite their transient nature, they have real effects and can influence other particles' behavior. Quantum fluctuations aren't just a curious aspect of quantum mechanics, they played a critical role in the universe's formation. During cosmic inflation, these fluctuations were stretched to macroscopic scales, magnifying the tiny fluctuations in the universe's density and leading to the large-scale structures we observe today. The patterns imprinted in the cosmic microwave background radiation directly result from these quantum fluctuations. Under certain conditions, quantum fluctuations can lead to creating real particles. One scenario occurs near a black hole's event horizon, a phenomenon known as Hawking radiation. Stephen Hawking proposed that quantum fluctuations at a black hole's edge could result in particle-antiparticle pairs, with one particle falling into the black hole and the other escaping into space. Another context where quantum fluctuations lead to particle creation is during cosmic inflation. The magnification of quantum fluctuations during inflation implies that virtual particles could freeze into real particles, contributing to the universe's matter content. This process underscores the interconnectedness of quantum mechanics and cosmology, revealing the quantum underpinnings of cosmic evolution. The role of energy in particle formation. Energy acts as the catalyst transforming the potential within quantum fluctuations into the material constituents of the cosmos. This process is rooted in Einstein's famous equation, E equals mc squared, which posits that energy and mass are interchangeable. This fundamental principle underscores the deep connection between energy and particle creation. In the vacuum of space, what appears empty is actually a seething cauldron of energy due to quantum fluctuations. These fluctuations allow for the creation of particle-antiparticle pairs. Although these pairs typically annihilate each other almost instantaneously, under certain conditions, they can become real particles. The conversion of energy into particles is a cornerstone of our understanding of the early universe. In the high-energy conditions following the Big Bang, the universe was a hot, dense soup of energy. As it expanded and cooled, some of this energy condensed into particles, following Einstein's equation. The early universe went through various phases during which the fundamental forces separated and the building blocks of matter formed. Energy not only facilitates particle creation but also influences their interactions and the structures they form. For example, the energy released during nuclear fusion in stars is responsible for synthesizing heavier elements essential for life. The Heisenberg uncertainty principle and particle creation. The Heisenberg uncertainty principle states that it's impossible to simultaneously know both a particle's exact position and momentum. This inherent uncertainty isn't due to experimental imperfections but is a fundamental universe property at the quantum level. The uncertainty principle relates intimately to particle creation, particularly regarding quantum fluctuations in the vacuum of space. The vacuum isn't empty but teems with virtual particles that continually pop into and out of existence. These particles exist temporarily, borrowing energy from the vacuum due to allowances made by the uncertainty principle. The principle permits these fluctuations by allowing temporary energy conservation violations. This temporary energy borrowing makes it possible for particle-antiparticle pairs to form spontaneously. Although these pairs usually annihilate each other almost immediately, their brief existence directly results from the uncertainty inherent in their positions and momenta. In certain extreme conditions, such as near a black hole's event horizon or during the early universe's rapid expansion, these virtual particles can become real, observable particles. This process of particle creation from the vacuum, facilitated by the uncertainty principle, highlights the principle's crucial role in the quantum world's dynamics and the cosmos's fabric. The first particles and forces. In the initial fraction of a second after the Big Bang, the universe was too hot and dense for any particles or atoms to exist. It contained a quark-gluon plasma, where quarks weren't confined within atomic nuclei but were free in a soup of gluons. As the universe expanded and cooled, quarks could coalesce to form protons and neutrons. This epoch, known as the Hadron epoch, occurred within the first microsecond to 1 second after the Big Bang. The formation of protons and neutrons marked a pivotal moment in the early universe. Following the Hadron epoch, the universe continued cooling, leading to the Lepton epoch, lasting from about 1 second to a few minutes post-Big Bang. During this period, leptons, such as electrons, were the dominant form of matter. The most critical event related to particle formation came next, nucleosynthesis, occurring within the first few minutes after the Big Bang. During this period, protons and neutrons began combining to form the simplest elements nuclei, hydrogen, helium, and trace amounts of lithium and beryllium. Separation of forces. Initially, in the universe's first moments, all forces were unified in a singular force. As the universe expanded and cooled, this primordial unity fractured in a series of symmetry-breaking events, leading to the distinct forces we recognize today. Gravity was the first to separate, emerging as the universe cooled from its hot, dense state. This separation is hypothesized to have occurred just a fraction of a second after the Big Bang, marking the universe's first step towards complex force interactions. Gravity's decoupling set the stage for the cosmos's large-scale structure. Following gravity separation, the grand unified force, encapsulating the electromagnetic, strong, and weak nuclear forces, persisted in its unified state until further cooling. As the temperature dropped to a critical point, the strong nuclear force distinguished itself from the electro-weak force, a combined form of the electromagnetic and weak nuclear forces. This separation laid the groundwork for the universe's first particles. The electro-weak force continued governing the universe's energetic landscape until it too underwent symmetry breaking, splitting into the electromagnetic force and the weak nuclear force. This finalized the roster of fundamental forces, setting the stage for more complex particles and, eventually, atoms. The electro-weak epoch. The electro-weak epoch represents a critical phase shortly after the Big Bang, when the electromagnetic and weak nuclear forces were unified as a single force. This epoch occurred approximately between 10 to the power of -12 seconds and 10 to the power of -6 seconds after the Big Bang, when the universe was cooling but still incredibly energetic. During this epoch, the universe was filled with a hot, dense plasma of quarks, leptons, and their antiparticles, along with the electro-weak bosons that mediated the unified force. As the universe expanded and cooled, it reached a critical temperature, allowing the electro-weak force to undergo a symmetry-breaking event. This event led to the differentiation of the electromagnetic force from the weak nuclear force, a fundamental step in the universe's maturation. The Higgs mechanism played a crucial role during this epoch. The interaction of particles with the Higgs field endowed them with mass, a process central to the symmetry-breaking event that distinguished the electromagnetic and weak nuclear forces. The Higgs boson's discovery in 2012 provided key evidence supporting this theoretical framework. The quark epoch and hadronization. Quarks, the fundamental constituents of matter, are subject to the strong nuclear force. In the universe's nascent moments, this force acted as the glue binding quarks together in groups of 3 to form baryons, which include protons and neutrons. The process began when the universe cooled sufficiently for the strong force to overcome the kinetic energy that had previously kept quarks apart. In this cooler environment, quarks started interacting more closely, forming pairs and triplets that would evolve into protons and neutrons. A proton comprises 2 up quarks and 1 down quark, while a neutron consists of 2 down quarks and 1 up quark. The specific quark combination determines the particle's properties, including its charge. This phase wasn't just about forming these particles, but also about transitioning from a state where quarks could move freely to a state where they were locked within protons and neutrons. This locking mechanism is crucial for matter's stability. Without it, complex structures making up the universe couldn't exist. The hadronization of quarks into protons and neutrons set the stage for the next cosmic evolution phase, the nucleosynthesis era, when the first atomic nuclei formed. Nucleosynthesis and atomic formation. As the universe continued expanding and cooling, it reached a temperature conducive to the fusion of protons and neutrons. This epoch, occurring roughly 3 minutes after the Big Bang, was when conditions were right for nuclear forces to overcome electromagnetic repulsion between protons, allowing them to join with neutrons to form simple elements nuclei. Primarily, hydrogen nuclei fused to form helium, along with trace amounts of deuterium, tritium, and small quantities of lithium and beryllium. Nucleosynthesis set the initial abundance of light elements in the universe, proportions that remarkably agree with Big Bang theory predictions. These primordial nucleosynthesis events laid the groundwork for star formation. Stars, through their own nuclear fusion cycles, would later forge heavier elements essential for life and complex structures. Next came the formation of the first atoms. This milestone, occurring around 380,000 years after the Big Bang, marked the universe's cooling to a point where electrons could bind with nuclei to form neutral atoms, a period known as recombination. As the universe cooled, electrons began combining with hydrogen and helium nuclei to form the first stable atoms. This recombination process drastically reduced photon scattering, allowing the universe to become transparent for the first time. The photons released formed the cosmic microwave background radiation. The formation of the first atoms was a turning point in the cosmic narrative, paving the way for the universe's transition from a hot, dense state to a cooler, structured one capable of supporting complex structures like stars and galaxies. Stellar nucleosynthesis and element formation. Nucleosynthesis, the process forming the natural abundances of chemical elements within stars played a crucial role in creating the diverse elements observed today. Following the first atom's formation, the universe primarily contained hydrogen and helium. Nucleosynthesis provided the processes necessary to forge heavier elements, transforming the early universe's primordial simplicity into rich chemical diversity. Nucleosynthesis occurred in several stages, starting with the Big Bang itself. Big Bang nucleosynthesis produced the lightest elements, but this process couldn't account for creating heavier elements essential for life. The next nucleosynthesis phase took place within stars. Stars transform lighter elements into heavier ones through nuclear fusion in their cores. In a star's life cycle, hydrogen nuclei fuse to form helium. As stars age and their cores heat up, they can fuse helium into carbon, and in more massive stars, form elements up to iron through successive nuclear burning stages. Creating elements heavier than iron requires different processes, such as the R process, rapid neutron capture, and the S process, slow neutron capture, primarily during supernova explosions and in asymptotic giant branch stars' outer shells. The diverse elements forged by nucleosynthesis spread throughout the galaxy by stellar winds and supernova explosions, seeding interstellar clouds with materials needed for the next generation of stars, planets, and eventually, life. Particle accelerators and experimental physics. Particle accelerators propel charged particles to high speeds and collide them, generating conditions mimicking those just after the Big Bang. These tools allow scientists to investigate matter's fundamental properties and the forces governing particle interactions. By accelerating particles to nearly light speed and colliding them, accelerators enable researchers to break down atomic components, revealing particles and phenomena not observable under normal conditions. A particle accelerator uses electric fields to accelerate particles and magnetic fields to steer them along a specified path. When high-energy particles collide, they produce new particles, allowing scientists to study particle physics in extreme energy density environments. The Large Hadron Collider, LHC, at CERN is the world's largest and most powerful particle accelerator, designed to probe into mysteries such as the Higgs boson's properties and dark matter. Beyond scientific applications, particle accelerators have practical uses in medicine, cancer treatment and medical diagnostics, industry, materials processing, and art and archaeology, analyzing artifacts non-destructively. Particle accelerators have led to numerous significant discoveries, including the Higgs boson, confirmation of quarks' existence, and W and Z bosons. These discoveries have been crucial for validating theoretical predictions and advancing our understanding of the universe's fundamental aspects. Theory and experiment in particle physics. The interplay between theory and experiment in particle physics involves several key steps. Theoretical physicists develop models based on mathematical principles to explain particles' properties and behaviors and the forces governing their interactions. These models often make precise predictions about certain interactions' outcomes or previously unobserved particles' existence. Experimental physicists design and conduct experiments using particle accelerators to test these predictions. The detectors surrounding collision points capture and record the particles produced, and sophisticated data analysis techniques interpret the results. A significant aspect of validating theoretical predictions is reproducing experimental results. In particle physics, multiple experiments must observe the same phenomena under similar conditions, adding credibility to the findings and helping confirm they aren't statistical anomalies. The Standard Model of Particle Physics. The Standard Model describes three of the four known fundamental forces: electromagnetic, weak, and strong nuclear forces, and classifies all known elementary particles. It's a cornerstone of modern physics, representing scientists' best understanding of how the universe's fundamental constituents behave and interact. At its core, the Standard Model builds on quantum mechanics and special relativity, incorporating both into quantum field theory. The model categorizes elementary particles into fermions, matter's building blocks, divided into quarks and leptons, and bosons, force carriers. A significant Standard Model triumph was predicting and subsequently discovering the Higgs boson, a particle providing mass to other particles through the Higgs mechanism. This discovery at the Large Hadron Collider in 2012 filled a crucial model gap. Despite its successes, the Standard Model isn't complete. It doesn't incorporate gravity, described by general relativity, nor does it account for dark matter and dark energy. Additionally, the model's inability to incorporate gravity or predict elementary particles' masses suggests it's part of a more comprehensive theory yet to be discovered. Limitations of the Standard Model. While remarkably successful, the Standard Model has limitations marking areas where our universe understanding is incomplete. These limitations point toward new physics beyond what we currently know. One significant limitation is its inability to incorporate gravity. The discrepancy between general relativity, describing very large scales, and quantum mechanics, describing very small scales, remains one of physics' most profound challenges. Another limitation is the Standard Model's silence on dark matter and dark energy. Universe observations suggest about 85% of its matter content is dark matter, and dark energy contributes about 68% of the universe's total energy content. The Standard Model doesn't predict dark matter particles' existence nor account for dark energy's properties. The Standard Model also can't explain the matter-antimatter asymmetry observed in the universe. According to the model, the Big Bang should have produced equal matter and antimatter amounts, which would annihilate each other. However, the observable universe is dominated by matter. Additionally, the Standard Model doesn't provide a satisfactory explanation for neutrino masses. Initially, the model assumed neutrinos were massless, but experiments have shown they have a small mass. Beyond the Standard Model, dark matter and dark energy. Dark matter and dark energy are two profound mysteries in modern cosmology, representing universe components invisible and undetectable by traditional means but whose presence is inferred from their gravitational effects and impact on the universe's expansion. Together, they compose about 95% of the universe's total mass energy content. Dark matter doesn't emit, absorb, or reflect light, making it invisible to electromagnetic radiation and difficult to detect directly. Despite being invisible, dark matter exerts gravitational forces, influencing the structure and formation of galaxies and galaxy clusters. It acts as a cosmic scaffold around which visible matter congregates. Dark energy is a mysterious force driving the universe's accelerated expansion. Dark energy's discovery in the late 1990s significantly surprised astronomers who had expected the universe's expansion might be slowing due to gravitational attraction. Dark energy is thought to be a property of space itself, evenly distributed throughout the universe and not diluting as space expands. During the early universe, dark matter's gravitational pull helped amplify slight irregularities left by quantum fluctuations, leading to large-scale structures like galaxies and galaxy clusters. These structures created potential wells within which ordinary matter could gather and cool, leading to star formation. Dark energy, on the other hand, accounts for approximately 68% of the universe and influences its expansion rate. Unlike dark matter, dark energy doesn't cluster but is uniformly distributed across space, exerting a repulsive force counteracting gravity. Supersymmetry and string theory. Supersymmetry proposes a type of symmetry between two fundamental particle classes, bosons, force carriers, and fermions, matter components. According to supersymmetry, for every Standard Model boson, there exists a corresponding fermion partner, and vice versa, not yet observed. These partner particles are known as superpartners. Supersymmetry's allure lies in its potential to address several unresolved issues within particle physics and cosmology. One significant challenge it aims to solve is the hierarchy problem, concerning the vast difference in strength between gravity and the other fundamental forces. Supersymmetry suggests new symmetries in physics laws can stabilize the Higgs boson's mass against quantum corrections. Moreover, supersymmetry is a leading candidate for explaining dark matter. Supersymmetric particles, particularly the lightest supersymmetric particle, are stable, electrically neutral, and only weakly interacting, making them excellent dark matter candidates. String theory, another leading candidate for extending our understanding of the universe's fundamental constituents, proposes that elementary particles aren't point-like dots, but rather tiny, vibrating strings. The vibrational modes of these strings correspond to different particles. String theory inherently includes supersymmetry and predicts the existence of many new particles, including those responsible for gravity. Theories involving extra dimensions suggest our universe might have more than the three spatial dimensions we experience. These extra dimensions could be compactified and hidden on scales too small for current experiments to detect directly. While these theories are mathematically elegant and offer exciting solutions to the Standard Model's shortcomings, direct experimental evidence remains elusive. The role of gravity in particle formation. Gravity, the weakest yet most far-reaching fundamental force, exerts a profound influence on particle formation, shaping the cosmos from the smallest scales to galactic structures. While its effects are subtle in particle physics, gravity's role becomes increasingly significant when considering the universe's evolution and structure formation. Gravity's most direct impact on particle formation can be seen in star formation. As gas and dust clouds collapse under their own gravity, they create dense regions where conditions become favorable for nuclear fusion. The intense pressure and temperature in these nascent stars initiate hydrogen atoms fusion into helium, releasing energy. This fusion generates heavier elements essential for life. Gravity is instrumental in black hole formation, regions of space-time where gravitational forces are so strong that nothing can escape. In the extreme conditions near a black hole's event horizon, Hawking radiation predicts the creation of particle-antiparticle pairs from the vacuum of space itself. On a cosmological scale, gravity's role extends to the very structure of the universe. The distribution of matter, from filamentary structures making up the cosmic web to galaxy formation, is governed by gravitational attraction. This distribution determines the regions where particles can form stars, planets, and other astronomical bodies. While gravity's direct influence on individual particles is overshadowed by stronger electromagnetic and nuclear forces at small scales, its cumulative effect over cosmic timescales and distances is crucial for understanding the universe's evolution. Cosmic inflation theory. Inflation posits that the universe underwent an exponential expansion in the first fractions of a second after the Big Bang. This rapid expansion stretched the universe's size by many orders of magnitude almost instantaneously. Inflation was introduced to solve several problems inherent in the original Big Bang theory. One was the horizon problem, questioning how widely separated universe parts could have the same temperature when light hasn't had enough time to travel between them. Inflation explains this by proposing these regions were once close together before being driven apart by swift expansion. Another issue addressed is the flatness problem. Observations suggest the universe is remarkably flat, requiring fine-tuning of initial conditions without inflation. Inflation elegantly solves this by diluting any curvature in the early universe's fabric. Inflation also explains the origin of the universe's large-scale structure. The theory predicts tiny quantum fluctuations in the early universe were stretched to astronomical scales by inflationary expansion, serving as seeds for structure growth through gravitational attraction. Inflation theory is supported by cosmic microwave background radiation observations, which show patterns of slight temperature variations consistent with inflation's predictions. However, the theory also raises questions about what caused inflation to start and stop. Inflation offers a compelling explanation for the uniformity observed in the cosmic microwave background. According to inflationary theory, the observable universe expanded from a tiny, subatomic size to macroscopic size extraordinarily quickly. This rapid expansion means regions now on opposite sides of the observable universe were once close together before inflation drove them apart. These regions could come to thermal equilibrium before being stretched across the sky, explaining the CMB's uniform temperature. Antimatter and symmetry in the universe. Antimatter mirrors matter's properties, but with opposite charges. For every particle constituting matter, there exists a corresponding antiparticle making up antimatter. These antiparticles possess the same mass as their matter counterparts but have opposite electric charge. Examples include the positron, the electron's antiparticle, and the antiproton. When a matter particle encounters its corresponding antiparticle, they annihilate each other in an energy burst, typically producing gamma rays. This annihilation process demonstrates the equivalence of mass and energy. Antimatter has practical applications and implications. In medicine, positron emission tomography (PET) scans rely on detecting gamma rays from positron annihilation to create detailed body images. Understanding antimatter is crucial for addressing questions about why the observable universe appears composed almost entirely of matter, despite theories predicting equal amounts were produced in the universe's early moments. CP violation refers to a phenomenon where the combined operation of charge conjugation and parity inversion is not conserved. It means certain processes involving particle transformation into their corresponding antiparticles don't occur the same way when charges and spatial orientations are reversed. CP violation helps explain matter-antimatter asymmetry in the universe. If all physical processes respected CP symmetry perfectly, matter and antimatter would have annihilated each other completely after the Big Bang. The observed asymmetry suggests processes where CP symmetry is violated must exist, favoring matter production over antimatter. Philosophical and conceptual questions. Can we truly understand the universe's origin? As we delve into cosmology and particle physics, we uncover glimpses of the cosmic drama that unfolded billions of years ago. Yet, despite our best efforts, a veil of mystery shrouds the ultimate genesis of the cosmos. Theories such as the Big Bang provide a framework for understanding the universe's evolution from its earliest moments. But when we peer back to the very instant of creation, we encounter a realm where physics laws break down and our conventional understanding falters. It's a realm of extreme temperatures, densities, and energies, where space-time itself undergoes profound transformations. In our quest to comprehend the universe's origin, we confront human cognition limits and scientific inquiry boundaries. Can we ever hope to unravel existence's mysteries with our finite minds and empirical methods? Or are there knowledge realms beyond human understanding? Some argue that understanding pursuit is an inherent aspect of the human condition, driving us to explore and seek answers to existence's deepest mysteries. Others contend there are limits to what we can know, and some aspects of reality may forever elude our grasp. The concept of nothing in modern physics. The concept of nothing challenges our fundamental understanding of reality. In modern physics, nothing isn't simply matter and energy absence. It's a complex and dynamic landscape governed by quantum mechanics. In quantum physics, the vacuum of space is far from empty. It teems with virtual particles spontaneously popping in and out of existence, borrowing energy from the vacuum for fleeting moments before annihilating each other. This phenomenon, known as vacuum fluctuations, suggests that even in particle absence, space-time fabric is seething with activity. Moreover, the concept of nothing is intertwined with the universe's origin mysteries. The Big Bang theory posits that the universe emerged from a singularity, a point of infinite density and temperature. But what preceded the Big Bang? Was there truly nothing before the universe began its expansion, or are there existence realms beyond our current understanding? These questions challenge our scientific understanding and philosophical conceptions of reality, existence, and being itself. The idea that something could emerge from nothing defies our intuitive understanding of causality and creation. Yet, the quantum world regularly demonstrates phenomena that defy classical intuition, suggesting that our understanding of nothing may be fundamentally incomplete. Some theoretical physicists propose that what we perceive as a nothing may actually be a quantum vacuum state, a sea of potential energy that, under certain conditions, can give rise to particles and eventually to the structures we observe in the universe. Societal implications of particle physics research. Research in particle physics has far-reaching implications beyond the laboratory, offering numerous benefits to society. While the subject might seem esoteric, advancements made in particle physics have yielded tangible outcomes impacting our daily lives. One significant contribution is its role in medical imaging and treatment. Technologies such as PET, positron emission tomography, and MRI, magnetic resonance imaging, have roots in particle physics research. These imaging techniques are crucial for diagnosing medical conditions and guiding treatment plans. Additionally, particle physics has paved the way for advancements in radiation therapy for cancer treatment. Techniques such as proton therapy, which utilizes proton beams to precisely target tumors while minimizing damage to surrounding healthy tissues, have emerged from particle physics research. The World Wide Web was invented at CERN to facilitate communication among researchers, transforming how information is accessed and shared globally. Advancements in particle detector technologies have led to creating more sensitive detectors used in security screening, environmental monitoring, and archaeological exploration. Future discoveries in particle physics hold the promise of revolutionizing various aspects of our daily lives. Breakthroughs could lead to developing more efficient and sustainable energy sources, helping to address climate change and energy security concerns. Advancements in fusion energy research, inspired by plasma physics study in particle accelerators, could one day provide a clean and virtually limitless power source. Discoveries may also lead to advancements in technology and computing. Quantum computing development, which draws heavily from quantum mechanics principles explored in particle physics, could revolutionize fields such as cryptography, drug discovery, and artificial intelligence. Ethical considerations in particle physics. Particle physics research raises several ethical considerations that warrant careful examination. One such consideration is resource allocation. Particle physics experiments often require substantial financial investments and sophisticated technology access. Critics argued these resources could be better allocated to address pressing societal issues. However, proponents argue that investing in fundamental research can lead to unforeseen technological breakthroughs and long-term societal benefits. Another ethical concern is the safety of particle physics experiments, particularly those involving high-energy particle accelerators. While catastrophic events' likelihood is extremely low, some worry about potential risks, such as micro-black hole creation or dangerous radiation release. Researchers and regulatory bodies must carefully assess and mitigate these risks. There are ethical considerations surrounding knowledge dissemination and the potential misuse of scientific discoveries. Particle physics research often yields valuable insights into the universe's fundamental workings, with wide-ranging implications for technology, medicine, and other fields. There is a risk that this knowledge could be weaponized or exploited for harmful purposes. Additionally, there are ethical questions related to international collaboration and research findings distribution. Collaborative efforts among scientists from different countries are essential for advancing knowledge in this field. However, issues such as intellectual property rights and equitable access to research opportunities can arise. Scientists and policymakers must consider how to balance scientific progress benefits with the need to prevent misuse and ensure knowledge responsible stewardship. By considering these ethical considerations and engaging in open dialogue, society can work together to navigate particle physics research's ethical complexities and maximize its potential benefits for humanity. Conclusion: from nothing to everything. As we conclude our journey contemplating the emergence of particles from what appears to be nothingness, we are confronted with profound philosophical questions that transcend empirical science boundaries. The path from quantum fluctuations in the vacuum to the rich tapestry of galaxies, stars, planets, and life represents one of the most astonishing narratives in human understanding. We have explored how the universe evolved from an incredibly hot, dense state, how fundamental forces separated during cosmic inflation, how particles formed and coalesced into atoms, and how stars forged the elements necessary for complex structures. Yet despite our remarkable progress in understanding these processes, deep mysteries remain. The boundary between existence and non-existence, something and nothing, continues to challenge our most fundamental concepts. The quantum world reveals a reality where absolute emptiness seems impossible, where even the vacuum teems with potential energy and fleeting virtual particles. This suggests that perhaps nothing in the absolute sense may not exist at all. Perhaps, in the cosmic symphony of creation, there lies a deeper truth beyond the grasp of our current understanding, a truth speaking to the interconnectedness of all existence and the infinite potential inherent in reality's fabric. Could it be that particles arise not from a void of nothingness, but from the boundless reservoir of possibility permeating the cosmos? Ultimately, the question of how particles form from nothing invites us to contemplate our place in the vast expanse of the universe and to embrace the wonder and mystery surrounding us. It challenges us to expand our minds beyond conventional thinking confines and to embrace the boundless possibilities lying at the heart of existence. How do you think particles came to life? How did it all start? Share your thoughts in the comments below. Thanks for watching.